Hey guys, there are a couple more examples that we didn't get to in our notes. On page 15 specifically, we might not have in your class gotten to this problem about this thermostat in the Colorado cabin. So they want to make sure that the pipes aren't going to freeze. So she sets the thermostat to 50 degrees Fahrenheit. She buys a thermostat to record the temperature each night. And the thermometer is measured in Celsius. So all this data and all these summary statistics are in Celsius. We're going to use the fact that you can use this conversion factor of degrees Fahrenheit is equal to 9/5 of your Celsius measurement plus 32 to answer these questions. So I would like the average temperature put in degrees Fahrenheit. And then I want to know if it seems accurate or not. So I don't want to convert every single data point into Fahrenheit and then find the average of those. I just want to figure out if I'm doing this linear transformation, is that going to affect the mean? And if so, is it going to affect it by multiplying? Is it going to affect it by addition? Is it both? Is it neither? What's happening? So if you come back up, I don't have it filled out in mine, but if you come back up to your notes, we said that mean is a measure of center, and measures of center are affected both by the addition section and the multiplication. So adding or subtracting changes your mean, multiplying changes your mean. So to find the mean in degrees Fahrenheit, I'm finding my new mean, so I'm going to put x bar sub new, or I guess I could put x bar sub Fahrenheit. It's going to be found by applying this multiplication and this addition to the old mean. So that means 9/5 of the old mean, 8.43, plus 32. Because multiplication and addition change measures of central tendency. So when I put that in my calculator, I see 47.174. So my new average in terms of Fahrenheit, 47.174 degrees Fahrenheit, which seems like it's a reasonable amount. She set it to 50, the average is 47, but we got to be careful because if that's all we know is the average, it could be a whole bunch of 20-degree measurements and a whole bunch of 60-degree measurements that average out to 47, and that wouldn't be acceptable. So I'd also like to know the standard deviation. Now, standard deviation is a measure of variation, and we had said that measures of variation, meaning not measures of central tendency, measures of variation are only affected by the multiplication. So you don't have to add things. It's talking about how spread out it is. So to find the standard deviation of the Fahrenheit measurements, my new standard deviation, all I need to do is take 9/5 of the old standard deviation. So 9/5 of 2.27 tells me that my new Fahrenheit standard deviation is 4.086 degrees Fahrenheit. And as always, I want you to make sure you know what this stands for. This is saying that the typical data values, the readings that the thermostat gives every night, are deviating away from the mean by a typical amount, by a standard distance of 4.086. So some are above, some are below, but the distance they are above and below is 4.086. The 93rd percentile, the temperature readings, is 12 degrees Celsius. I want the 93rd percentile temperature in degrees Fahrenheit. Now, percentiles are measures of position, meaning this is the spot where 93% fall below. And we had said that when we are doing measures of center and location will be affected by adding. We also said here that multiplying affects, or dividing, affects measures of position, so measures of location. So think of it kind of like the median. Median's a location, it's also a center, but it's saying here's where 50% is below. So if I'm saying here's where 93% is below, it's going to be affected by both addition and multiplication. Sorry. That means I'm going to need to do 9/5 of the Celsius measure, and then I need to add the 32 still. So 9/5 of 12, which when you think about it, makes sense. If I had just given you a science problem and said, hey, here's the way you convert Fahrenheit to Celsius, and here's a Celsius measure, change it to Fahrenheit, you would have just plugged it in, no question. You would have never considered only multiplying or only adding. It's only when we start talking about measures of variation that we got to be careful of only doing certain ones. So this is saying that 93% of the thermostat readings are below 53.6 degrees Fahrenheit. So it's just kind of giving you a location for that. The other thing that we hadn't gotten to is looking at these transformations in terms of z-scores. Now remember, z-scores, you can call them standardized scores. They're telling you how many standard deviations you are from the mean. We find it with the formula of taking your data value, subtracting the mean, and dividing by the standard deviation. Which means when this is saying the test scores in example 1, so the last video that I made, these test scores here, it's basically already telling you the mean and the standard deviation without making you calculate it. I mean, you could, but why? So we now know that the mean of that data set has to be 35.44. And the standard deviation of the test scores, the typical distance, the scores are deviating away from 35.44 is 8.77. By translating it to a z-score, by subtracting and dividing, you're going to affect things. However, one of them is not the shape. We had said that the shape does not change no matter what you multiply, no matter what you add. Technically speaking, when you divide by 8.77, technically speaking, you are shrinking the scale of it, but that doesn't change the shape. It just makes it look smaller, smaller of the exact same shape. Center is changed, though. We're going over that measures of central tendencies are affected by addition, subtraction, multiplication, division, by everything. So the old center was 35.4. So the new one, I'm going to put x bar sub z, the mean of the z-scores, will be found by your old mean, 35.44, and then I'm going to apply those transformations. So I'm going to apply subtracting 35.44. I'm going to apply the division part of it. But anytime I subtract anything by itself in the numerator, I'm going to get 0, which means the mean of the distribution of z-scores because that's what we're talking about here. That's going to be 0. Because once you change a mean into a z-score, you're subtracting it from itself, you're going to get 0. Variability, though, so in this case, standard deviation is all we can talk about. If I look at the standard deviation of the z-scores, meaning what happens to the standard deviation after applying this transformation, standard deviation, the spread of your data, is not affected by moving it left and right. The only thing that affects it is multiplication and division, which is this portion here. So I just need to take the old standard deviation and apply the division. Well, it's saying to divide by 8.77, meaning the standard deviation of the distribution of z-scores, I'm abbreviating, going to be 1. That's going to be important because as we look at this next one here, when we apply what's called the empirical rule, we are using a distribution of z-scores. So mean, center, would be 0. And then I'm going to add and subtract 1 standard deviation from the mean. Well, adding 1 to 0 is 1. Subtracting 1 from 0 is -1. Or I could put a 2 and a -2. I'm color coding these for a reason, by the way. And what's one we can actually see? I think orange works well. 3 and -3. I think I just used orange twice. Whatever, doesn't matter. The empirical rule says once you have this bell-shaped data, which is what this is saying here, it's symmetric, but it has this smooth bell-type shape to it. If you have a data set that is told or found to be the shape, 68% of your data will lie within 1 standard deviation of the mean. So if I chopped this graph apart, living in this space would be over half your data. That's part of the empirical rule. If I go 2 standard deviations of the mean, I think I used that purple, you're going to have 95% of your data values. So that means if I chopped a little wider in this space lives 95% of the data. And if I go one out a little further, almost all of your data is there, 99.7%. So that means if I chopped almost all of your graph apart, what on earth did I do? The middle 90, okay, I guess I can't write on that line. The middle 99.7% is here, which is basically all of it. We're left with 0.3%. You can't see it. Like if I could zoom in infinitely close, you would never see that this curve actually touched this line. It gets infinitely close, which gets into calculus things, but all you need to know is it technically never touches, so you would still have space for the remaining 0.3%. It's just visually it doesn't exist because that's such a small amount of your data set. Before we do example 4, I'm going to do example 5. I should have reordered them, but I have a bunch of data, and I would like to first find the mean, variance, and the standard deviation. So I'm going to put them in my calculator. I'm going to 1-bar stats it. I just found that the mean is 41.5, and I'm going to change colors because I can. The mean of our data set is 41.5. This is representing salary, so it's like $41,000, $41,500. And I found the standard deviation is about 5.3. So about $5,300. So then the variance, this is just a practice in the fact that it exists. You take that 5.3 and you square it. You're going to get an even more rounded value because you're squaring a rounded value, but it's around 28.09 thousand. So I'd like to summarize this by stating how much the middle 68% of your employees make. I also should have told you this was bell-shaped. Let's pretend I made a better example than this. So pretend that you know it's bell-shaped.